I'd like to introduce Jelmer NEEVEN from Plumerai. Jelmer is a deep learning scientist and software engineer with a passion for building smart tools and real-world AI applications. He's obtained an MSc in AI from Maastricht University and has been with Plumerai for 3 years. He spends his time building efficient, robust AI for microcontrollers through researching novel model architectures, data techniques, and training methods. Take it away, Jelmer.
There you go. Great. Thank you, everyone, for joining today, and thank you for the great introduction. So I'm going to be talking to you about cultivating the perfect data diet, to feed to your tiny models and hopefully grow them into a robust product. But first, a brief introduction to Plumerai. We're a startup focused on efficient deep learning in general, but we're mostly working on computer vision right now. And one particular application relevant in this context is our people detection product. And this is a production-worthy computer vision product that runs on edge devices like ARM Cortex-A SoCs and even on low-power $1 Cortex-M microcontrollers. And you can see some examples of it in action there. And you see that despite being efficient enough to run on these tiny edge devices, it is still very accurate. And you can imagine that this is very useful for things like monitoring desk occupancy in offices, automated heating control, web conferencing, smart doorbells, security cameras, you name it. By the way, if you want to see it live in action, then come check out our booth afterwards, because we've brought some demos with us. So how did we manage to build a tinyML product that is both efficient and robust? Well, there's various elements, and they're all highly intertwined. So to do it well, you need to cover the entire stack. And in our case, that means that we have our own hardware IP core, which we've also brought a demo of. So definitely come check out the booth. We have our Plumerai inference engine, which is actually world's fastest inference engine for ARM Cortex-M. It is 1.6 times faster and uses 2 times less RAM than TensorFlow Lite for microcontrollers, so that really makes a difference. We, of course, have custom tiny model architectures and training strategies. And then finally, we have the Plumerai data pipeline, which is what I'll be talking about today. And interestingly, the importance of quality data is often overlooked by the deep learning community. People tend to focus on other things, like architectures, for example. But good data is absolutely crucial for developing an actual product, and even more so for tinyML, as I will demonstrate later. But why all this talk about data pipelines? Why not just use a public data set? Well, here you see some examples of the visual wake words data sets, where the images on the left are the ones without people, and the images on the right are the ones with people. And this looks quite convenient. You may think, OK, this looks suitable for training a people detection model. But there's various issues with this data set. So for example, for the negatives, the context itself is often irrelevant. So the image on the top left is a toothbrush, and you can quite quickly see that there's no person there, simply because you don't usually find tiny people on top of bathroom sinks. So the context kind of gives away the label of the image here. And an interesting example of that is the traffic light in the bottom there. Because we found that because our models are tiny and efficient, they have limited capacity, and this makes them prone to taking shortcuts. And in this case, it found that in this data set, the sky is usually blue, and the sky also usually doesn't contain any people. And so it would predict whenever there was a large blue background that there weren't any people there, which was a valid shortcut to take on this data set, but is, of course, not very valid in real life. Another issue, not just with this data set, but with public data in general, is that it's often scraped from the internet. And that means that any image in there must inherently be interesting enough for someone to have uploaded it there in the first place. And for these positives, that means that there's quite obviously a person there, and the person is really the center of attention of this image. But of course, for an actual product, that may not at all be the case. So we used this exact data set to develop our initial prototype, and we designed an architecture around it. It worked amazing on paper, and we quickly found that it was absolutely useless in real life. So the lesson we learned quite quickly was that before we could design a good model, we very first needed to design a good data set. And of course, we did. We built our own Plumerai data set, which you can see here. We used it to train the models I've shown you in the first slide, so we were a lot more successful with this. And your question is now, of course, well, what is then the big difference? And you can see that our images here are not person-centered. So for each of these images, the focus is just on the room itself, and there's no contextual clues giving away whether there are any people or not. And in fact, some of these images are plain boring. So the one on the bottom left, literally half of that image is a wall, which is not exactly something people tend to upload to Instagram. But it is, of course, exactly the kind of environment that your product might operate in. And we've been collecting these images ourselves, but just collecting the images is not enough. If you really want to build a quality data set at deep learning scale, you also need good data tooling to ensure that the data, and therefore the model, are both as good as they could be. And that brings me to the Plumerai infrastructure. So here you see the two components that together receive about 90% of the attention of the deep learning community. And here you see the actual set of components that we have working together. So you see that you need a lot more than just those two to build an actual product. And you see that some of these are highlighted in light blue, and that means that they're data related. So you see that of all our infrastructure, almost half of it is data related. So the data really is important. I'd like to talk about all of them in detail, but I can only cover the ones in the top right, unfortunately, here. But let's start with the data unit tests, because data unit tests are the very first thing you absolutely need. People tend to evaluate models by computing, for example, the accuracy on some data set, but that doesn't tell you where your model is doing well and where it's not doing well. And what I mean by data unit tests are small but very specific collections of data that should cover all the things you expect to encounter on a regular basis. So for example, for us, this means that we have a unit test with pictures of empty desks, and we have a unit test also of people walking through hallways. And the goal here is to kind of approximate the real-world performance of your model, because you want to have some guarantees that your product is going to behave as intended. But another part of your unit test should actually be the exact opposite. It should cover edge cases. So for example, we have a plant unit test. And you may not immediately think about plants when you think about person detection, but we found that one of our initial models tended to mistake large office plants for people. And we have, of course, solved this problem, but we also have a unit test for it now so that we can verify that for every model we ship in the future, the problem will remain solved. And then once your unit tests are in place, you want to go through your training and validation data, and you want to make sure that it aligns with your goal. So in other words, you need to curate your data set. And you need good data tooling to do this. So the very first thing your tooling needs to allow you to do is simply identify where your model is not behaving well. So you need to identify failure cases. And this can be very simple. The simplest form would just be visualizing your model's mispredictions. And luckily, most data tooling today does allow you to do this. And then once you've identified a failure case, you'll immediately create a test for it so that you can quantify your performance on this failure case, and you can measure your progress towards solving it. And then the next step is where it gets interesting, because now that you've identified a failure case, you need to somehow link this to your training data. And this is what sets our own in-house data tooling apart from most off-the-shelf data platforms. The question you want to answer here is, what part of my training data is making my model misbehave in practice? And this is a quite open-ended process, but some examples of techniques we use are looking at visual similarity, training a little interactive classifier, and looking at images that strongly influence the training process. And I'll give you a demo of some of these techniques in the slide after this, so stay tuned. But for now, once you've found a problem in your training data, you of course want to address it. So depending on the problem you found, you may either want to correct some labels, you may want to oversample some data, you may want to apply some targeted training strategies, or you may simply want to add or even remove data. And removing data is a lot more valid than it sounds, because the quality of your data is a lot more important than the quantity. And then, of course, once you've addressed these problems, you'll rebuild your data set, retrain your model, re-evaluate it on the test that you created in the first step, and then depending on how well you're doing now on your problem, you'll probably go through the cycle a few more times. So it's definitely an iterative process. Then for the demo I promised. So one of the techniques I used is looking at visual similarity. So imagine that we found out that something has gone wrong during labeling, and some of the plants in our data set have ended up being labeled as people, but we don't know quite which images. One thing I can do is simply take a quick picture of a plant with my smartphone, and then I can upload it in our custom data tooling here, if I can enable this little video. Yeah, can you start it? Yes, thank you. So I can just press the little search icon here. I'll upload an image that I've taken in my home office of the plant there, and it's going to show me all the images in our data set that look similar. So it's going to show me, hopefully, other plants. And here we see that it works, and luckily these plants have not been labeled as people, so we're now a little bit more sure that our data is correct. But we could go more specific, so let's look at all plants that have flowers. We can select the ones with flowers, and we can train a little classifier. And in the beginning, it's not going to be very good. It's mostly just going to return plants and not necessarily plants with flowers. But we keep selecting the ones that do have flowers. We keep going through the data, and then we train the classifier again. And you'll see that quite quickly it gets the hang of this. So already after just 2 iterations, most of the images here are indeed plants, flowers. So we can now tag the ones that do have flowers. We can open up a little tagging menu, and we can now modify some information in our database to keep track of the fact that these are flowers. So assume that our model had a problem with flowers. Now we know which images are flowers. We can modify our training strategy, for example, by oversampling these images, and we can now resolve this problem. And here you can see that they've now been tagged for future reference. Another technique I mentioned is looking at images that strongly influence the training process. So here I've selected some images from our data set. And if I now enable the predictions of one of our older models, if that's kind of, yeah, there we go, you'll see that it makes some mispredictions. And if we look at the image on the left there in more detail, you see that it thinks there's a person there, but it's actually just a bar stool with a jacket on it. So we can select this specific misprediction and then find the images in our training data set that contributed to this specific problem. And for example, we've been training on this image here, which has two clearly visible people and one hidden in the back there with a green box. And if we look at some other examples, we've also trained on this image. And again, there's someone hidden there, but it might as well be a backpack. It's very difficult to see. Or we've trained on this image, where essentially we just see shoes and a bit of the legs of someone, but it's very dark. So overall, I would say these images are way too difficult, and they're confusing our model. So again, we select the images, we open up the tagging menu, and we add a tag for future reference, and we can now use this to modify our training strategies. And in this case, I would say that we just remove these from training altogether, at least for the time being, for this specific model, and that should hopefully improve results. But it's important to keep in mind that just finding problem cases and tagging images is only the first step. This is only useful if you then use this information to actually modify your training process. So to recap, our tooling allows us to identify problematic images in various ways, and some examples I've shown are looking at similar appearance. So given a quick picture taken with my smartphone of a plant, I can find all the other plants in our database, or at least some other ones, and then I can verify that they've been labeled correctly. Given that a model has a problem with a specific kind of image, so let's say that it has an issue with flowers, then I can train a little classifier and keep tuning it until it finds all the flowers in our database. We can tag them, we can oversample them, and we can hopefully resolve that problem. And I can look at images that strongly influence the training process. So given the problematic image on the left, I could find the image on the right, which is in our training data set, but should probably be removed because it's reducing our model quality. But actually, the most important thing our data tooling allows us to do is simply act on our findings in real time. We're not just exploring the data set and writing down our findings, but as soon as we find anything problematic, we can find more images like that, we can tag them, and we can immediately modify the training process. But also very importantly, this is fully custom in-house tooling, and this allows us to quickly add and explore new AI-assisted approaches like the ones I've just demoed. And these are actually essential for making this whole data iteration process scalable. Because in our case, we have roughly 30 million images in total, so that means we have terabytes of data to go through, and we simply couldn't build a quality data set of deep learning scale without these AI-assisted approaches. So we need a custom tooling to do this. So to conclude, our tiny models are not just efficient, but they're still very accurate, and building production-worthy tinyML like that requires vertical integration. Developing good tinyML applications is a puzzle with many moving parts, and to do it well, you need to make sure that everything works together nicely. And specifically, this vertical integration is what allows us to do rapid iteration. So as soon as we find any kind of problem with our model, we can have a look at the data, we can identify problems there, we can fix the problems, and then only once we have a high-quality data set, then we can finally train a high-quality model. And it seems I've gone through quite rapidly, so I have one more slide, but let's take some questions now, and then I'll show that at the end. So I think we have 6 minutes or so.
Yeah, thank you very much, Jelmer. It's nice to actually have a deep dive into data. We always talk about the networks, but the networks without the data, you know, you can't do it without the data. Are there any questions on the floor?
It's a really interesting method to train a classifier around certain selected things. What's the real turnaround time for this selection and retraining of a classifier to find similar cases, you know, plants with flowers, etc.?
Yeah, so it depends a bit on the kind of the difficulty of the class you're trying to assess. So the flowers, for example, are fairly straightforward. So you could see that just it's a very small classifier in this case, and just after a few iterations, it was already pretty good. But sometimes the problematic cases are more tricky. So Sometimes it's a combination of lighting and some shadows and specific objects. Then you would probably need a larger classifier and a few more iterations. But so far, we found that we could invest, let's say, an hour, and it would find us thousands of images way beyond the scale that we would be able to find manually by just looking at all of them, brute force.
Great, thank you.
Oh, yeah. Can you give a clue on how you achieve finding a specific image in the training data set that caused a certain mistake in inference?
You want to know how that works?
Yeah. Roughly, if it's...
Yeah, it's, so we actually, it's a quite involved process, but we keep track essentially of the gradients during training, and then we can build a matrix from those, and then we can feed that specific problematic image to our tooling. We'll compute the gradient essentially, and then we'll compare the gradient of all the other images in our database. And then essentially the question that we're answering is here, if we would train the model on each of those images one more time, how much would that influence, like would that increase or would it decrease the loss? And then the thing we're visualizing here is show me the images that would increase the loss maximally if we would train on them again. And these tend to be quite problematic.
Yeah, very interesting. Thank you.
Yeah, thanks. This is really interesting to kind of, bring in garbage in, garbage out paradigm for tinyML. The question I have is, the tooling, sort of how your tooling can kind of, address like a macro issue rather than, sort of, all the examples that you sort of highlighted, right? There was something visually you could tell. But let's say, often a good example is for this, where you could have a lighting problem, right, in your data set, right, where one sort of class is actually learned because of a macro feature that you cannot tell until you see multiple of the images, right? And then, so how is there something you has come across that can address an issue like that?
Could you explain a little bit more about the specific kind of issue?
Examples that actually long time I heard in a keynote speaker that there was a class where they were trying to figure out, the tanks, right, versus no tank, and all the tanks picture were taken on a daylight versus non-daylight, right, and actually neural network learned to figure out between daylight versus no daylight, and there you need to look at, multiple of pictures, right, to figure out what's the issue is. So I'm just wondering, like, based on the tooling and experience, what you have done, is there some method or technique that can help?
So still, even with these techniques, I must say it's a bit, it's a bit open to interpretation. It's definitely, there's kind of some training going on the engineering side as well. Like you need to really get familiar with what do we kind of see when we go through the data. And yeah, some problems are very straightforward. For example, the one with plants, we quite quickly saw that especially large office plants, and we had some shadows going on, those tended to be mispredicted by one of our older models. But we also see quite difficult things like, you have some suspicion that there is like some unifying pattern across all the images that you're seeing, but it's very hard to put in words. And those are definitely harder to solve as well. But so far, it has helped us a lot to find those kinds of problems and then reason about where might we be going wrong. So for example, actually, the initial model I mentioned that we trained on the visual wakeward data set, there we saw that mostly we had issues that were quite hard to describe. And it turned out that we had designed a very efficient model architecture that was downsampling quite aggressively, and therefore it ended up looking at textures. And the textures are kind of problems that, we just had like little black blobs across the image, and those would then somehow trigger a misprediction. So yeah, it remains a bit tricky to really pinpoint what's going wrong, but definitely it can give insights into things like that.
Okay, yeah, thanks again.
Thank you very much, Jelmer.
All right. Then for the final slide. So you can have the brightest engineers, a state-of-the-art model architecture, and a huge cloud budget, but if your data looks like the one in the bottom right, you're not going to use it to train a good model. Like the person just now said, garbage in, garbage out. He may be a vegetable, but he's not part of a healthy diet. And he is actually part of a public data set. So if there's only one thing you take away from this talk today, let it be not to take your data for granted. Thank you.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymex, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, Pixart, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.